We have here three gentlemen, three speakers who are going to talk about the same. The first one will be Mr. Rick Barker. Rick Barker is a principal, Barker Mohandas from USA. Can I invite you, Rick?
The title is Improved Techniques for Vertical Transportation, or VT, for super tall buildings. We're going to talk about the technique for two super tall projects with multiple sub-towers. The same techniques applied to a super tall tower with a central core, the basic lift equipment for the long travel shuttle lifts, and our studies to help the lift manufacturers expedite the remaining R&D they need for the shuttles. A little bit why we can do that. We've been in business 10 years. However, our key technical team has 25 years on average prior experience, not just in VT system design, but in lift product R&D, engineering, innovation, and contracting for tall buildings. We've opened a company in India. P.S. Lyle, who's here today, is leading that company. Some project team credits for projects we're going to show quickly. Some projects we're doing in Asia and the USA. Most of these are under construction. One listed, not shown, as a new project in Mumbai, a series of 3 tall towers with Lota developer. Projects in the Middle East, some are under construction. We're going to talk a little bit about the two on the top right. We've been involved with projects with sky bridges and sub-towers somewhat even before our inception. Our co-founder, Mohan, who's also here today, was involved start to finish at Otis with the Petronas Twin Towers. You'll see renderings from competitions and a developer's design. The two on the right proceeded through detailed design. The one on the far right proceeded to ground. Quickly, one of the competitions was with KPF, included the skydock elements of the system. Gensler won this competition. This proceeded through detailed design. It was initially called Palm Tower, later called El Burj, was with Pei Partnership Architects. D.D. Pei's concept was for 3 sub-towers connected with sky bridges. The architect was looking to let the light in. The structural engineer was looking to let the wind through. We were looking to the sky bridges to allow multiple access paths and egress paths for emergency. And also, if there's enough levels to those sky bridges, we could stack up some of the local lifts. It was primarily all apartment occupancy in one of the design stages. I'll just summarize the basic system design features. It achieved space efficiency and high performance. It's easy to have space efficiency by cutting lifts. This achieved both. A high capacity back of house and emergency transport, redundant vertical circulation, in part enabled by the multiple sub-towers and sky bridges. The refuge floors could be redefined as evacuation floors. Nakheel was the developer of that. Did not proceed with that project. They proceeded in the Nakheel Harbor Tower, different location, new architect, Woods Bagot. However, Nakheel insisted that the concepts of multiple sub-towers and emergency circulation from El Burj be carried forward into the Harbor Tower. Site work was started. In fact, half of the friction piles were completed. You see a very happy lift consultant on the left. I've been working on this project so long, it finally proceeded to ground. Included 2 or 4 sub-towers, depending on the section. The bottom 2 sections were in halves. The next 3 sections in quads, rejoined in the halves. It was an optimization between the number of lifts needed for the type of occupancy in each section and the structural/wind engineering. You see the profile of the tower relative to Burj Khalifa and some other famous landmarks and designs. At each sky bridge, there was a protected 360-degree protected access to all sub-towers and all lifts and all stairs that intersected this combination refuge and evacuation level. As you can see in concept, you could go multiple directions, horizontally, vertically. The occupancy stacked up as follows. There was the equivalent of 2 46-story office buildings in the base, an 800-room hotel, very large common areas, 3 sections of apartments in quads. That's 12 25-story office buildings, and rejoined at a hotel, luxury hotel, and observation deck levels, the top and midway. This is an elementary diagram of the passenger lifts, the shuttles and locals. There are duplicate lifts for the offices and the apartments due to the walking distances involved, including at the car park where we used electric walks or travelators, and at the sky bridges. So the tower was about, as I recall, 95 meters in diameter. The system was, the hotel drop-offs allowed for a central group of shuttles to each of the hotels. The system was based in part on travel limits that were determined for a single-deck shuttle, a double-deck shuttle, or a large goods shuttle. Our SkyDock system, again, elementary diagram, is shown behind the scenes. We'll talk about this in a moment. In what the simple diagram represent the lifts, which totaled, the main lifts in the tower were 124 primary lifts. If you count the double-deck cabs, 150 lifts total, excluding any two-stop elevators and escalators and so forth. To understand the techniques, we'll talk about an actual design but not disclosed for a 165-floor central core tall tower. You could take elevators higher than what's shown to enable a kilometer tall, but the essential elements are shown. All the lift stops and all the lifts are shown in the diagram at the left. A very similar occupancy mix, some office in zone 1, hotel going up, and then 4 zones of apartments, and similarly observation decks halfway and at the top. I'll talk about the simplest element to achieve high capacity and efficiency. Double-deck lift obviously achieves a high capacity for its footprint. When you have the lift travel halfway and it hands off its load to a connecting set of double-deck shuttles, it can return in less time, full speed for another load. It's a very big boost in throughput capacity for its footprint. By the way, just the main stops, which are 2 for each connecting pair of lifts, are shown, but we'll talk about other stops later. A unique technique is for the apartment passenger lift system. There's one group of 6 shuttles. They're destination-based. They stop at 4 sky lobbies, which you see, and they connect with 4 groups of 3 local lifts. The hoistways are stacked up on top of each other. Again, just the normal stops are shown. The benefits is very space, cost, and construction efficient. As you can imagine, the formwork would quite simple, straight up. Space savings is critical. We have so many other lifts involved in the tower, and we also need to leave room for very important back-of-house lifts, goods lifts that are also used by firefighters. Same simple wayfinding. You get all sky lobbies. You walk out of the shuttles directly into the locals. It appears as though the shuttles make 4 stops. The dispatching will reduce the actual shuttle stops. We'll cover that a little bit later. They won't stop at all 4 sky lobbies. If one shuttle in a group of 6 is out of service, 5 remain. It's a shared transportation system for sure. However, we could have a special VIP operation for a few residences. If a car is empty and available, we could assign it to a few people. The standard local lifts stacked up with no express zones available from any elevator company. This same system could be converted into a 3-zone system. 4 zones are shown here. Let's compare it to some conventional techniques. You have an idea of the space footprint. If we were to have separate shuttles to each sky lobby, instead of 6 shuttles, we'd have 12 shuttles. Conventional lifts out of the main lobby simply don't work for a tall building, so designers often focus on some type of sky lobby technique, sometimes top-down, where passengers actually need to travel up to egress the building, unless design provisions are made to handle that differently. Advantages, though, there's a separate shuttle group for luxury apartment zone, clearly, and normally the shuttles would just have 1 stop above the main lobby. Having just 1 stop, if that's the only stop, can also be a disadvantage, as we'll talk in a moment. As I said, it's very important, we think, to save space in the apartment lift system to leave room for the remaining lifts. The amount of goods staff, etc., sky dock levels, sky lobby levels need to be carried in such a building. We need a very high performance back of house system. We've called this a sky dock system. Similarly, it's a handoff system. Leg one, a group of 3 shuttles, has basically one stop at a sky dock. It simultaneously hands off its load to connecting goods shuttles that go to another sky dock. It tends to be every other MEP level, simultaneously transferring to top-down a local goods lift in each zone. Local goods lift gives each apartment zone a little bit of privacy. They can have their own amenities at a sky lobby and so forth. During an emergency, if you can imagine, all of these green arrows revert to down arrows. The terminal stops of the local lifts, as you see, they overlap, so you can have a path down the tower independent of the shuttles. We're trying to provide very high capacity and also redundancy both for back of house and emergencies. Here's some ideas of the capacity. Just carrying containers one direction or 2 direction, could be widgets, boxes, anything. But we thought it was interesting to look at what's the people carrying capacity in the down direction. The leg one shuttles tend to determine the capacity. They're the critical path that can be shown. Conventional goods lift, the problem is we've probably taken so much space with conventional apartment lifts that there's very little room left for conventional goods lift. If our estimate, at least in this design, is that we would only have room for a pair of conventional goods lifts serving the apartments. They would express from a ground dock up to floor 50, serve all stops through 130, and then transfer from there. And you can see the capacity is significantly less, especially in the emergency mode. If we were able to fit a group of 3, the capacity is somewhat more, but still falls short. The Skydock system, Mrs. Smith carrying her lamp up to floor 135 is just not an effective use of the system. So wheeled containers are very important on the shuttles to the Skydocks. Automated guided vehicles can boost the effectiveness. They can move the containers, lift up under the containers, come in from offline loading areas, which are good for security screening. Here's a system diagram again. All the stops are shown. We circled what we call rescue stops that stop at a combination refuge and evacuation floor at these key nodes at each sky bridge. The idea is to bring as much of the entire system capacity to bear to pick people up on the way down. We think having lifts go through an express zone from here to 400 meters or 500 meters and picking up nobody on the way is a mistake. The stops in the express zones are also very useful to detune ropes for sway. We'll talk about it a little bit if we have time. The techniques really enable a core that stacks up. Again, all the lifts for this central core, super tall tower, 165 typical floors, common floors. All the lifts you see are shown in the core. The worst case is it cut near the ground. The core gets smaller as you go up. The key elements are all the goods lifts are a combination firefighters lifts. They're co-located with stairs. And you can see this element of 360-degree access to all lifts with lifts intersecting that go by this combination refuge and evacuation level. The point is you don't need multiple sub-towers and sky bridges to apply these techniques. There's a couple improvements we'd like. But here's the performance for the apartment passenger shuttles we just talked about. This is, and we'll also talk about the codes and how they apply to these techniques. Most architects and owners are familiar with destination dispatching, available from all lift manufacturers. We think a particularly good application is the multiple sky lobby shuttles. If a lift is serving 4 sky lobbies going such distances, it comes down and everybody wants to get in, it's probably going to stop at every sky lobby. However, if these guys are going to sky lobbies 1 and 3, and they're going to sky lobbies 2 and 4, we'd assign you to separate lifts, and as you can see, the effect would be fewer stops, and likely less travel. Here's some simulation results, again, of the 6-car shuttle group serving multiple sky lobbies, just comparing the dispatching alone. Same shuttles, putting a different controller box on. Long waits are improved, lobby queues, and so forth. Just a quick point on the speeds. We were basing this on 10 to 12 meters per second, whatever the manufacturer would have available in their motor power. The down speed was variable. Published metrics for ear comfort, that's a rapid recompression of the atmosphere you'll feel in your inner ear. What is this on the... Thank you. A published metric which we can calculate and follow is 2,000 pascals is ear pressure differential. So if we went top to bottom, full speed, 12 meters per second, would be very uncomfortable and quite painful, actually. So we've reduced the speed. If we're going a full descent, 7 meters per second, no problem. We can meet that comfort threshold. However, we still want the full speed for a 2-sky lobby run, and could go full speed at that time. Here's what's happening behind the scenes with 2 of the shuttles in the group. Conventional dispatching is stopping at about 2.5 sky lobbies per direction. It's not stopping at all 4, but it's still somewhat inconvenient to passengers in the lifts. With destination dispatching, the sky lobby shuttles are stopping at about 1.5 per direction. Less stops, less travel means less energy. The same shuttle group with a different controller box is taking less energy. It's not saving. This is just a 15-minute simulation period. However, if you recall, with the traffic performance was such we probably needed a 7th shuttle, which would add more energy. However, if we revert to conventional techniques, we need 3 to 6 more shuttles plus additional hoistways, concrete to build the hoistways and so forth. The approach to codes, we think it's harmonized, forward-looking, and practical. The U.S. has finally improved its model codes that now offer some improvements, long waited for. We've had to long look to the UK, who deserves a lot of thanks for protecting a firefighter's lift, co-locating with stairs. However, the codes in the UK were founded at least 20 years ago in a very low-rise London, and having a passenger lift serving all floors, reaching the top nonstop in 60 seconds is just simply impractical, technically. Also, if buildable, that hoistway would lack redundancy and provide very low handling capacity. It also complicates reverse stack effects, smoke management designs. The transfers in the Skydock system boost through capacity significantly, as you saw. They provide restaging areas for emergency personnel, larger cabs for stretchers. And when we bring the whole system capacity to bear on these rescue stops to get people out, we think it's a better plan. Wheeled containers can also get goods out of the way, especially if they're automated with the use of AGVs. Techniques need to be part of an integrated cross-discipline fire protection plan, usually led by the fire protection engineer. Basic lift equipment for the shuttles. We need the largest lift machines available. Here's some pictures from 4 manufacturers. I won't go over all the numbers. The bottom line to some of the machine and roping and other considerations, a single-deck shuttle, we think the practical rise limit is about 600 meters, a double-deck shuttle about 450, and a single-deck goods shuttle somewhere in between. The machines are very large for the building industry, but they're only large in the building industry. These are mine elevator machines. They're not exactly machine roomless lifts. They have their codes are a little less stringent, though. The shuttles also require the largest capacity safeties, rails, ropes available. That basic equipment is generally available from a limited number of lift manufacturers, but is available. Our studies we were commissioned for is to help the lift manufacturers expedite the remaining R&D they would need for the shuttles. Do not assume they've developed all the issues and products for this type of building. Lift solutions for aeroacoustic ride vibration are well known and they're fairly well developed. The design team needs to take measures to address 2 of them. One, mitigate, get rid of that. the design team needs to take measures to reduce reverse stack effect. It's traveling counterflow to a high-speed lift going up. You see in the bottom left, it's a lift in that core plan you saw. We've actually violated our own rule to avoid single hoistways. However, we've massively over-increased the hoistway size to decrease the speed of the surrounding air, to the point we estimated with aerodynamic shrouds and double-wall cabs that acoustics could be acceptable. Special roller guides are needed to reduce ride vibration at high speed. There's a diagram of active roller guides. Our chief engineer, Dr. Skalski, led the Otis development in prototyping of active roller guides. Rope sway, it's often talked about, and there's common solutions to some degree for tall buildings. These are a few of the basic ones. One is to alter the free rope length. The rescue stops we talked about earlier, if you have a lift traveling from ground to only from ground to 500 meters, there's no stops in between, the length of that sitar or guitar string is the frequency will remain the same. However, if you change the fret down to every 25 floors, you'll detune it. It'll sound lousy, but be out of resonant with the sway period of the building. That's a very simple solution. It's also good for emergency egress. Next step solutions, our studies found the traditional follower carriages used in the World Trade Center and the Sears Tower are of little effect to no effect as the travels went higher. Depending, it could even be following between a vibration mode of the ropes. So our point, they also add quite a bit of weight, and there's reliability issues with them. So our studies were, without suggesting a proprietary solution, there's a patent I left at Otis and a patent by structural engineer Les Robertson. You don't need a proprietary solution, but there's other solutions available for that. Very important also for the sway issue, such shuttle lifts have traveling cables below the lift, multi-conductor traveling cables. During building sway conditions, these traveling cables can be entangled in the compensating ropes and pull out, and the car can shut down. This is not a leap forward in R&D. Use wireless communications and inductive power rail systems. The equipment is available from companies like Wampfler. It's already used very successfully in outdoor lifts, incline lifts with shorter rises, and every day in automated people movers in airports where the horizontal travel is 1 kilometer. One of the last studies was spring effect of long ropes. This, I won't go over every element here. A couple of the lift companies had indicated a nonstop descent of 600 meters is going to cause leveling problems and holding the car at the floor when passengers are trying to board. We modeled it, or he did, in MATLAB, which we use sometimes, both the controls, the electrical mechanical solutions. And the bottom line is we could show to the lift companies, we think it's a solvable solution. You could hold the car within minus 4 millimeters of floor level after a 600-meter descent. This last special study goes back to the birth of the high-rise building and the elevator. It was provide a ropeless governor on the car. This avoids relying on a long governor rope and a remote governor in the machine room and dealing with some of the rope dynamics involved. If you can imagine the situation that was likely to occur at the World Trade Center, this would have been a good improvement. And my partner, Paul Bennett, who led safety development at Otis, reminded me, and he says, now what if the smart electronic governor fails? He said, Rick, the patent model you have in your office, it's allegedly 160 years old, to put a spring inertial trip device to actuate the safeties on the bottom of the car in case that fails. So these are the kind of things we felt were not leaps, important applied technologies. Okay, very useful. Summary. Conventional techniques in some codes appear strained for super tall buildings. We think the VT techniques presented offer significant building benefits for such buildings. A comprehensive system approach is needed, considering other disciplines and issues. Additional engineering is needed for lift equipment and controls yet developed, and multiple skills are needed to determine the VT technique and applied technologies. Thank you.